Good afternoon, and thanks very much for inviting us to talk about the work of the TEDC group and our work on tiny targets. I'm sort of looking around and I can see that several of you have heard this story before, so hopefully there's something new in it for you. So, yes, we also struggle saying those words. So we again call it sleeping sickness, or human African trypanosomiasis. And so, just to give you a little bit of a background, very briefly, what is the problem we've been attempting to solve. And the disease is sleeping sickness, and it's caused by trypanosomes, which are single-cell protozoa, blood parasites, and they are transmitted by tsetse flies. And this disease has had three, in the time of school's history, it's had three pandemics or epidemics. The disease is only found in Africa and had one at the turn of the last century, of the end of the 1800s, early 1900s, and two in the last century. One in the 1940s and one in. Thank you. Okay. So and one in the late 1990s, and each of those is associated with huge upheaval in Africa. Initially to do with the colonization, then in the middle of the last century during the war, and then civil war, strife, political instability across Central Africa. So the figures reported here, the WHO figures from 1940 through to 2000, generally there's at these peaks of these epidemics, there were about 30 to 40,000 reported cases. So these were people that were treated for the disease. WHO estimates that something only like 1 in 10 people was ever detected. So this is a fatal disease if untreated. So 9 out of 10 people died of this disease. And so that represents, at its peak, something like 300,000 people dying a year, only in a few countries across Central and West Africa. So casting, again, given the circumstances, I thought, again, might remind you that the beginning of the scientific story of trypanosomiasis started with a person that was born and raised in Bedlington, just across the water on the Wirral. He was educated as a clinician at the University of Liverpool, and he was part of the very early expeditions to Africa to start to analyse what was causing these various tropical diseases. And he went to the Gambia in 1902 and with the team there made the very first description of trypanosomes in someone working on the river, in fact a European. And in the archives you can still see this report. It's amazingly, given that this was just after really sort of all these parasites were being described, and already he's picking up features of the disease, speculating how it's transmitted. At that stage they didn't realise it was tsetse flies were transmitting it, but he also refers to work in southern Africa where tsetse were implicated in the animal disease. So it's a very, great piece of work, and that really started the story that I'll be talking about. So Gambian sleeping sickness. So the trypanosome that Everett Dutton described in the Gambia was a T. brucei gambiense, and that causes the most common form of the disease. And it is a zoonotic. It's a tsetse fly, an uninfected tsetse fly, bites an infected human being, develops in the tsetse, and then subsequently that fly might bite an uninfected human, and the cycle continues. It's only found, this particular form of the disease is found only in Central and West Africa and transmitted by riverine tsetse. So that's what you can see on the right. This is the distribution of riverine flies. And this disease, still today, has no vaccine, no prophylactic drugs. It's fatal if it's not treated. And until quite recently, the treatments for it were also extremely dangerous and toxic. Something like 1 in 20 people treated for the disease would die of the cure. So although it's over quite an extensive part of Africa, in fact, it turns out that only about 5 countries are severely affected by this. Only 5 countries have 95% of all the cases. In particular, the DRC, where over 2/3 of all cases occur, and then Angola, Uganda, South Sudan, and the CAR. So a swathe of countries across Central Africa. So in 2012, at the London Declaration, sleeping sickness was included in the declaration of the global effort to eliminate neglected tropical diseases. So this graph shows you where we were in 2012. So the numbers of cases a year had gone down from that epidemic in the late 1990s and down to about 7,000 cases a year. And at that London Declaration, the community declared that they would aim to eliminate the disease as a public health problem across Africa by 2020. And in a subsequent meeting, declared that they would aim to actually eliminate transmission. So there should be no cases by 2030. So hugely ambitious cases, an ambitious plan in very difficult countries. So there were many sort of details to these metrics, but one of them, the sort of outline figure, is that 2,000 cases by 2020. So you can see we've got about 5,000 cases a year, so there's still quite a lot of work to be done in 2012. So the tools we used at that time were the screening and treating, so mass screening of people, finding who's infected and treating them with these relatively toxic drugs. I'm just showing you in the graph there the picture for the data for the DRC, which represents most of the cases. And you can see in that time, it's gone down from something like 25,000 cases in the DRC down to about 1,000 or so by 2018. And just look at the blue line there. That's the number of people being screened. So from about 2004 to 2018, that's 2.5 million people being checked yearly for that disease. So a massive effort in a very difficult setting. So the numbers are going down. Would this achieve those elimination goals? So Cat Rock, a group of modelers at University of Warwick, our partners, modeled what was happening in the DRC. And what this map shows you is blue areas are health zones which are going to be eliminated. They're going to eliminate the disease by 2030. And all the red areas are places where we're not going to hit that target. So her work, along with other studies, sort of sets the agenda for how can we achieve that goal. We're not going to get it doing what we currently do, even though we're making progress. And her work indicated that the way we can really accelerate this process is by adding vector control. So were there any tools at that time in about 2010 for controlling tsetse flies? Well, in East and Southern Africa, some very potent, user-friendly, relatively cheap tools have been developed. So on the left there, yes, it's on your left, is a target. It's a piece of cloth baited with artificial attractants. Tsetse flies regard this as an artificial host, like a cow or a buffalo. They're attracted to it, they land on it and pick up a lethal dose of insecticide. So these targets are distributed through the environment evenly over quite large areas and have been used to, for instance, control tsetse in Zimbabwe, Botswana, South Africa. An alternative method is, rather than have artificial cows, you have the real thing. You treat cattle with insecticide. Again, tsetse are attracted to those cattle and are killed. So we had the tools, but it turns out these were not the right tools for the work we needed to do in Central and West Africa for the vectors of Gambian sleeping sickness. The trouble was, first of all, the odors didn't seem to be effective for these particular riverine tsetse. The targets, big, bulky, quite complicated, expensive things, were difficult to deploy, especially the high densities that you needed to use if the attractants weren't effective. And in many of the countries like the DRC, cattle are not a part of the rural economy in the same sort of way they are, say, in Ethiopia and Tanzania. So we had tools, but they just weren't effective for the areas where we were working. So at that time, about 2005, we started to put together proposals, initially to the European Union and also to the Bill and Melinda Gates Foundation, to address that problem. Could we develop new tools that would be usable, practicable, clean, but effective against the riverine tsetse? So we went back to basics. What we intended to do was look at in the same way the attractants used for savanna tsetse, which were the the smell of a cow. We wanted to look at what were the odours that might be present in the hosts of riverine tsetse. So one of the important hosts, for instance, is a monitor lizard. Other important hosts were pigs, humans. So again, analysing their odours, extracting them, testing them, and seeing whether they were effective. We also went back to baker's eggs and looked at the visual responses of tsetse flies, of these riverine tsetse. So really very basic discovery research, insect behaviour, done in the field, quite remote settings across 5 different countries. The upshot of 5 years of work were tiny targets. So this is a tiny target developed in collaboration with our industrial partners. So the idea is these are distributed along rivers, river edge where riverine tsetse concentrate. They are attracted to this blue colour. But what they tend to do is they'll come to it but not land on it. And then so on the side of it, we have this netting is impregnated with insecticide. The flies collide with that. They can't see it, so they're just colliding with it accidentally, pick up a lethal dose of insecticide, fly off and die, probably within about half an hour of that happening. There's no attractants with this because none of the odours that these sort of flies do not seem to respond to host odours. So the initial work was done across several countries, and then we did the very first trials in Kenya, Uganda, and Guinea. And I just want to give you an example of the sort of results we had in these very early stages. So this is in about 2015. So in Uganda, so in each, what I'm showing you here is a graph of the numbers of tsetse, though that's catch index, against months after deployment. So on the left-hand edge, the very first number is the numbers at the beginning, and we're expressing everything as a percentage or an index of that initial catch. So by definition, 1. And as you can see, the numbers go down to something like 0.05. So we're getting something like 95% control. Just putting these targets out, flies come to them and are killed. And it wasn't just an effect of something was happening in the environment. The insect graph in the middle there is in a neighbouring district in Koboko, and there you can see the numbers fluctuate up and down either side of that red line, which is the catch index of 1. So it looks as though the deployment of targets has driven these fly numbers down to very low levels. Moving to another focus, the Mandul focus in Chad. And here again, by the beginning, it starts off at 1, and then you can see just 2 little blue dots where numbers of flies are very, very low. But this might also look like a pretty useless monitoring scheme, but actually what happened was we were going out and catching literally no flies after repeated investigations. And that sort of has continued to this area, still an area of control. We catch many years no flies at all. So this technique has an amazingly profound effect and rapid effect on tsetse populations. So building on those sort of early trials, these are then expanded. So by the end of 2020, these are the sort of numbers that were being deployed. And if you think the very first target put out, small island, Lake Victoria, in 2011, has now gone up to these sorts of numbers. So 21,000 square kilometres covered, 2.5 million people protected, and those people are in those, again, if you remember at the beginning of the talk, I was talking about just a few countries have this disease, so that's where the focus of our work is. So we're working, really covering a large percentage of the people threatened by this disease. So we're putting out lots of targets, we seem to be having a lot of impact on tsetse. What's the evidence that we're impacting on the disease itself? So the very best example, I think, is in the Mandul focus, which was the second example I showed you. And just to go back to those initial results, so the pink vertical bars are where we deploy targets just once a year, and the dots are the numbers of tsetse, and the dashes are places where we sampled and didn't catch anything. So again, you know, we've got this really massive decline in abundance. And we had the case data from this particular focus going back from 2000, and the group at Warwick then fit this to their model and then produce a model, and then when we put out targets in 2013, they then use their model to go forward and say, well, if we had done nothing, there were no targets, just kept on doing the same old screening and treating, what would have happened? And that's what you see there, those red the red bars, the red box plots, and the yellow ones, a slightly strengthened health system, numbers would go down, but not as fast as to meet the sort of goals that we were looking for in elimination. But if we actually deploy the targets as we did, then the numbers become vanishingly small. So again, that's blown up into, so you can see that's about predicted 8 new cases a year as opposed to hundreds. Subsequent analyses by the same group, it looks like we probably interrupted transmission in 2015. There have been no new cases since in this particular focus. So that's the sort of story that's been happening across lots of these countries that have adopted tiny targets: Chad, Uganda, Côte d'Ivoire. Numbers of flies are going down. These are the numbers of cases across the country, also going down to very low levels. So Uganda hasn't had any for more than any cases at all in the last 4 years. Côte d'Ivoire in the same sort of position. So we've had an impact on disease, and with this, the method has become adopted in both national and global policies. So the WHO document talking about what we're going to do over the next 10 years specifically mentions vector control as part of that strategy to eliminate the disease and meet that 2030 goal. So 3 countries have also declared elimination of the public health problem. So that was the 2020 goal. Another country is expected to declare early next year, and 2 countries will probably declare elimination of transmission in 2025. So this is where we are today. We're about something like 10% of where we were at the time of the declaration. Just 675 cases a year reported. Again, there'll be more cases actually happening, but even the ratio of reported cases to unknown is changing. So it probably represents something like less than 2,000 cases globally. Those 3 countries have declared elimination. Are we going to hit those 2030 goals? So I think one really important thing that gives us optimism that that ambitious goal could be realized is it's nothing to do with entomology or entomologists or tsetse flies, but the development of amazing new drugs. So in the past, it was treating sleeping sickness was a two-week intravenous course, spinal tap to get the diagnosis in very remote settings, extremely difficult problems of resistance. In 2018, oral drugs became available, effective for all stages, a 1-week course. Next year, what we're expecting is approval of this latest form, Cosiborol, extremely well tolerated, single dose. You could now probably, the anticipation is that you'll be able to treat people on just suspicion of infection. It's so safe. And so I think this could well change how we're going to manage the disease and the prospects of really eliminating it. So that's the optimistic view of what might happen. But of course, there are some things, you know, it would be, you'd surely say, oh, come on, Steve, it's not that good. So yeah, there are some challenges that lie ahead. I think first of all are some of the things that have happened over the last decade, the sort of global shocks that happen both nationally and globally. So for instance, the COVID pandemic affected how teams could deploy, screen people and treat them. In West Africa, the Ebola epidemic, both in Guinea and in the DRC, had severe effects. So I've just shown you, I showed you those 3 graphs earlier showing how the numbers are going down. In fact, Guinea was one of the 4 countries to start adopting tiny targets right at the beginning. And in their case, you can see they don't show that nice, smooth downward trend. They have a blip. There's a slight downward bit where the whole screening system collapsed during the Ebola crisis. Then, of course, once that's reestablished, we can find there's lots more cases. So we hope, of course, these sort of shocks don't happen, but they're highly likely. The other one is a sort of technical thing, as the numbers are going down a little bit like with guinea worm. As the numbers go down, some other features of the disease become apparent. So there is some evidence that there seem to be healthy carriers amongst the human population that have got trypanosomes, can infect vectors, might be allowing the disease to persist in a community where there's no apparent cases. Similarly, there might be animals might play some sort of role in the transmission of this parasite. I think we have tools to deal with that particular problem. And the last one, again, as we get closer and closer to those no cases, we'll get down to very low numbers. We'll be spending a lot of money, and that will be challenging to maintain that. So these are that listing, I think, are the sort of bits of our success story that are nothing to do with science. You know, we've had strong partnerships. We've had people in the Gates Foundation, WHO here in the UK shouting for vector control and work on TEDC. We've had collaboration across different disciplines, social scientists, economists, modelers. We've got industrial partners. So everyone has to be still working together in a case in the times when perhaps there aren't many cases and funding will be difficult. So I've just got two slides here, one looking back, just a sort of brief reflection on this story that I've just related to you, and sort of fitting it in with the school's mission about translational research going from discovery to policy. So one of those things, I think, is how long that takes. You know, we were probably talking about this as an idea, starting to write a bit of a proposal in about 2005. So it's taken us 20 years to do this. And I think, you know, there's the partnerships and a funder that's been willing to stay with us all that time. Right at the beginning, Bill and Melinda Gates Foundation made a significant contribution, and they are still with us today, and even this week, Andrew and others are writing proposals to get us to the 2030 goal. So looking ahead, what will we be doing at the school and with our partners? So first, it's helping those countries achieve those elimination goals. Also expanding the countries where we're currently working in, the geographies, expanding to the neglected tropical disease countries. So places like Cameroon, Congo, Equatorial Guinea, Gabon, they have sleeping sickness, but they don't have any programs that include tiny targets at the moment. We hope we can change that. And then sort of thinking further ahead as we get down right to the end game, when there were apparently no cases, like the case of Uganda, they had stopped doing any vector control. So how do we monitor for that? What do we do if and when we do find there are cases still there, perhaps imported from South Sudan or DRC by movement of populations? And can we even work with other parts of the community which are also still concerned about tsetse flies and trypanosomes because it causes animal disease? Can we leverage the work of farmers, agriculture, and together protect humans? So just as a concluding slide to where are we? Should we be optimistic? Can we reach that 2030 goal? So I think we have many reasons to be optimistic. Several countries are approaching their 5 years without disease, without any cases, and are on track to have elimination of transmission. In all those countries, we have very much strength and capacity. We have tools at work. The countries can achieve these sort of goals themselves. And we also have the prospect of even better tools in prospect, with, in particular, better drugs. Reasons of caution, concern, to keep on going. So that 5-year elimination criterion is many countries still getting cases. So we are not going to hit that 2030, there's no disease, for sure. We just haven't got the time to do that. There will undoubtedly still be insecurity and conflicts in some of the countries we're working in and that still have this disease. Again, how do we overcome sort of donor fatigue, national fatigue, as other health systems think about more pressing problems? And as we approach the end and that post-elimination period, how do we keep capacity so those countries are still vigilant and still know how to and have the capacity to respond to cases should they occur? So, as you can imagine, 20 years of work is literally hundreds of people, tens of institutions, tens of researchers at the school. So I've just listed most of the people I hope at the school are listed there and those in bold and are in bold, because I might bump into them and they might ask, why wasn't my name there? So thanks for your attention, and good night.